Hey guys, so today I just want to talk about calculus for integrations. So the basic concept of differential calculus we covered in the preceding chapter. This chapter will be devoted into integral calculus, and which is the other broad area of calculus. So as you may notice that calculus involved with limit, derivative, and integration. And here's the one. So the antiderivative of function f of x is a new function f of x such that df of x over dx equals f of x. And then we do have two different type of integral. So in general, so one is called indefinite. So that means once you integrate it, you need to put in the family c at the end. It's a constant. And then definite integrals, always giving you the exact value of the integration. So basically definite integral as area under the curve. So let's say that you want to approximate the area under the curve. So this one is called the Riemann sum. So we can use that the right endpoint or the left endpoint, or the trapezoidal rule or the Simpson's rule for doing the approximations for the area under the curve. So let's say that I try to summarize all the area of the rectangles together. So that would give you the area under the curve. And the exact area as the definite integrals. So this one is just a definition. Integrals of from a to b, either f of x or y dx. So equals that the summations, sigma, yk times delta x. Yk, that means the different height of the rectangle. Delta x, that's the interval width. And then since we take the limit, delta x goes to dx, so we can find out the area under the curve. And then definite integral with variable, upper limit, lower limit. So upper limit, it's integral from a to x, y dx. And more proper form for the dummy variables, we can use that integrals from a to x, y of u du. And then area under the straight line of a segment. So basically we just find the area of the trapezoid, area of the another trapezoid, and other area of a trapezoid. So this one basically just like an area of a trapezoid's formula. So 1/2 times y2 plus y1 times the difference from x2 minus x1. So the way to find the area of this y trapezoid, so the height, and also the different distance from x1, x2, so the height, and then y2, y1, which is the upper length or the upper base with the lower base. So basically it's just like a geometric concept, the way to find the area under the curve. And also this one too, finding the area under the curve or the line segment. So we do have a square, triangle, and then the rectangle. So once you integrate that, the area from 0 to 10, or 12, excuse me. So we just want to find out the area of a square, which is 2 times 20. And then the area of a triangle, so this one is 2 times negative 20, and then 1/2. And also this one is 12 times 2 times 1/2. So once you add all the areas together, so that would be the integral. The area of the line segments. So once you add them all together, so the total area would be 10. So 40, that's the area of square. And then the area of triangles, so which is negative 20. Well, the area over here is nothing, so the area of a triangle, another 20, because that they're symmetrical. And then over here is nothing, and then area of a rectangle is negative 10 times, well, the difference of the distance, which is what, 10? Well, excuse me, that's 3, okay? So once you find that, so negative 10 times 3, so it's negative 30. So once you add them all together, so it's 10. So the guideline, so if y is a non-zero constant, integral is either increasing, decreasing linearly. If segment is triangular, integral it's increasing or decreasing as a parabola. If y equals 0, integral remains at previous level. Integral moves up or down from previous level. Example, no sudden jumps. Beginning and the end points are good reference level. So here's the one that we just did. And here's another similar problem. So we can find the area of the trapezoids, and then a quarter of a circle, another quarter of a circle. With that, the area of the composite figure, and also the rectangle, and also the trapezoid, and also the rectangle. So here's the tabulations of integrals. So pretty much that means the exact same thing. And this one is the part 2 of fundamental theorem of calculus. So integrals from a to b. So once you integrate it, we got f of b minus f of a. So here's some of the formula that you need to recognize. Those are the basic formula. So let's say that's the coefficient. We just integrate that f of x. So a times capital F of x. And then since you do have multiple terms, you can always separate them to integrate it separately. And then the power rule, that's the one we use most often. So anytime they integrate x to the power of n, it's x to the power of n plus 1 over n plus 1. And then integrals of e to the power of ax is just e to the power of ax over a. Integrals of 1 over x, which is natural log of x, sine of ax, which is cosine of ax, but don't forget to multiply by the missing coefficients, negative 1 over a, and then cosine of a, integrals that as sine of ax, and then the missing coefficient is 1 over a. And then sine square of ax, there's like a special formula for that, or we can use integrated by part, which is 1 half x minus 1 over 4a sine of 2ax. And this one is more complicated formula that, well, you don't need to recognize all this. This one is just like can be applying using the different kind of integration technique. Okay, so which we'll talk about that in the future. And in example 7-3 through 7-5, well, it depends on the textbook that you're using. So determine the following integral in each case. So here's one of the examples. So let's say that you integrated from 12. Well, it's a indefinite integral. So there's no boundary, there's no upper bound, lower bound here. So we got 12 e to the power of 4x integrated. So we got 12 times e to the power of 4x over 4. So basically that one's just using that kind of like a missing coefficient rule, and then plus constant c. And then simplified it, we got 3e to the power of 4x plus c. And as you may notice, that derivative of e to the power of 4x, which is the same as 4 times e to the power of 4x. So 4 is missing, so that's why we need to divide it by 4, the inverse. And then here's another example. So I try to use the formula. So that one would be considered 12, which is the coefficients. And then using the formula, it's 1 over a squared times sine of 2x minus x over a times cosine of 2x plus constant c. And then the rest of this, you can just simplify it. So again, it's about applying the formula that we just talked about from the previous slide. And also this one can be done with the integration by part technique, and which is the part of the calculus BC stuff. We'll talk about that in the future. And here's one of the general examples. So integrated by the separation terms. So we got integrals of 6x squared dx plus integrals of 3 over x dx. So integrals of 6x squared is 6x to the power of 3 over 3 by using the power rule. And then, as you may notice the pattern here, so integrals of 1 over x is natural log of absolute value of x. So this one is missing with the absolute value, supposed to be with the absolute value of x. So 3 is just the coefficient, we can just pull it out. And don't forget at the end, it's a indefinite integral, so we need to add the constant c. So this one is just like a general principles for integration. So here's another example. So we integrated sine of x from 0 to pi, so it's indefinite integral. Well, this one is definite, excuse me. So once you integrate it, sine of x is negative cosine of x. Now, for this one, there's no need to add the family c at the end. So basically, we just use the part 2 of fundamental theorem of calculus. So f of b minus f of a. So negative cosine of pi minus negative cosine of 0. So cosine of pi, by using the unit circle, you may notice that's negative 1. And then cosine of 0, that's also negative 1. Well, it's 1, but it's negative times 1, so it's negative 1. So negative, negative, positive. So negative, negative, positive, so it's 1 plus 1 is 2. So that would be the area of a sine of x curve. So that's the area from 0 to pi. And here's another example. So for a times x to the power of e to the power of negative 2x. So this one can be done by using integrated by part. So once you integrate it, and then we plug in that the lower bound and the upper bound. So once you plug in a number, you do end up with 2e to the power of negative 2 times the quantity of negative 2 times 1 minus 1. And then minus 2 times e to the power of negative 0, 0 minus 1. And then combine the like terms, simplify the whole thing. Eventually, that's about 1.188. And this one should be the approximation symbol. And here's one of the traditional problem for displacement, velocity, accelerations. Acceleration is always represented by a of t, can be done with the unit meters per second square or square second. And then the other one is velocity, it's meter per second. And then the positions, displacement in meters, so it's meters. So dv over dt is velocity, derivative of velocity is acceleration. And dv equals dv over dt times dt, so that equals at times dt. So once you integrate that, the accelerations, so you'll get the velocity. Okay, so this one is just in general, so integrated accelerations, at dt plus c1, so you'll get the velocity. And this one is just the derivations. And once you get the integrals of velocity, you'll get the displacement. And contract, so v of t, it's just the integrals from at dt from 0 to t plus v of 0. And then y of 0 is from 0 to t, vt dt plus y of 0. So we'll finish the other lessons for the next video. Thank you for watching it today.